Good afternoon, everyone. The guest has arrived. So welcome, sir.
Yeah, thank you. Thank you, sir.
Yes, sir. The last session of the day of five days FPP is here. I welcome Dr. Venkateshwaran from Rajalakshmi Engineering College. Welcome, sir.
Thank you, sir. Yeah.
Sir. On behalf of Hindustan College of Engineering and Technology, Department of Aeronautical Engineering, myself, Veeramanindan, as a moderator, I am welcoming you again. And I request now Diksha Sambyal to deliver the intro of the guest speaker.
Good afternoon, everyone. I'm profoundly delighted to take an opportunity to introduce the chief guest of the session, Dr. N Venkateshwaran. Dr. N Venkateshwaran is currently working as professor in mechanical engineering at Rajalakshmi College of Engineering and Technology. He has completed his doctorate in the area of natural fiber composite with AICT scholarship at Anna University. He has published more than 50 papers in international journals, 4 book chapters in the area of natural fiber composites and additive manufacturing. He also has published 3 books in the area of CAD, CAM, CIM, and material sciences. He has a research citation of 2000 with H index of 19 and I index of 24 and is identified by Thomas Reuters as top 2 percentile researchers in the area of research based on citations. He has received research funding worth of rupees 20 lakhs so far and was included in the Marquis biographies of Who is Who Achiever in the year 2012 and 22 for the research contribution. Thank you so much for joining us today, sir, and we are grateful to have you, and we hope we'll all get to learn a lot from you. Thank you.
Yeah, thank you. Thank you for the introduction. So due to bandwidth, I will bandwidth connection for. Am I audible?
Sir, audible.
Yeah. Okay.
Yes, sir. It's loud and clear.
Yeah. Okay. Thank you. Due to the bandwidth connection and other related networking issues, so I will stop my video presentation. Right. As of now. Okay. So I will let me make the presentation. I hope my screen is visible now.
Yes, sir. Yes, sir.
Yeah, thank you. Yeah, so before getting into the topic of nano clay is influencing the properties, especially the mechanical and thermal properties of polymer composite. So let us understand the basics of what is the material, right? And why we are going in for a nano material, or what is the need for this nano sized material, etc. Okay, so basically any materials have been classified as either as metallic, composite, ceramics, then we will have electronic material, polymeric material, biomaterial, nanomaterials. So these are the general classification of the materials as of now. Again, based on the structure, they may be either crystalline in nature, polycrystalline, or amorphous in the nature. As we know, they may be either crystal structure, or they may have more than one crystals, or it will be amorphous in the nature. And in these nanomaterial, okay, so included in which one of the dimension will be in the nanoscale. Then we call that material as a nanomaterial. It may be either the thickness, it may be either the diameter, it may be either the length. So of this, one of the dimension will be in the nanoscale. Then we call it as a nanomaterial. So again, basically they have divided into as 0 dimension, that is nanoparticles. Then we will have 1 dimension So we will have nano wires, tubes, nano rods are some of the examples for one-dimensional nanomaterial. Then we have two-dimensional film. That is the thickness of the thickness will be very, very smaller. And also some kind of coatings that we are making over a steel alloy, or it may be over a polymers. And then 3D materials, so which is bulk or some of these nano materials. The materials may be categorized as 0 dimension, 1 dimension, 2 and 3 dimensions. Okay, so what is this 0 dimension, 1 dimension, 2 and 3 dimension? So it is based on the direction in which the confinement of the material took place. Okay, so based on the nature of the confinement, whether they are constrained in all the direction, that is all x, y and z direction, then we call that it as a 0 dimension. And examples are nothing but the nanoparticles. So all the nanoparticles are 0 dimensions in nature. And 1 dimension, so in which one of the dimension, right, either it may be z or it may be x and y, so of which one of the dimension is confined to a nano, especially since we are using the rod, wires and tube, the diameter, usually the diameter of the material will be of nano size, especially 100 nanometers. So then we can able to classify it as a one-dimensional material. And a two-dimensional material, so the materials are confinement on two axes, x, y or y, z or any of the two planes. So in which, so some of the examples are films which we are developing for the biomedical application or wound application, or the films, nano films which may be used for water barrier, gas barrier applications, filtration, water filter, or the absorption of oil spill. So those are some of the examples of nanofilms. And nowadays these nanofilms are being used in the mobile phones. And the 3D is nothing but a three-dimensional object. So where this nano composite will formed as a three-dimensional. So all the three x, y as well as z will not be of confined to any region. So if we compare the thermal conductivity of the carbon nanotubes, so nanotubes are usually a two-dimensional nanomaterial, so which is of 3000 watts per meter per Kelvin, whereas the copper, a bulk copper is having only 400 watts per meter per Kelvin. So if we are comparing the thermal conductivity of the carbon nanotube and copper, so the copper is nearly 6 times more than the copper material what we are seeing or what we are using it now as one of the best thermal conductivity material, whereas the carbon nanotube, so which is nearly 6 times better than the copper, okay, are available. And next, so this 1 dimension or 3 dimension, how the shape will be, right? The shape usually for a 3-dimensional object will be spherical in the shape, okay. So and some of the examples are TiO2 and SiO2 in nanoscale. Okay, so these 3-dimensional nanoparticles are spherical in the shape, and some of the examples are nano TiO2 or nano SiO2. Then we will move into the 2-dimension, so which is nothing but nanotube, rod, wires, right? So carbon nanotube, nanoclays, and a nanofibrillated cellulose. Cellulose from the plant fibers. The cellulose is one of the main constituent which gives the strength to the plant fiber. So when the cellulose has been, we will have a 1-dimensional, right? It may be either a platelets. They are some of the examples are graphene nanotube, hexagonal boron nitrate, bentonite clays, are some of the examples of a nanoplatelets. And so why these nano materials have been used, or on what factors these nano materials are depending on, or provides us the better property. So here we are comparing material, that is, which the size of the material will be either macro or micro in the size, right? So these properties, that is the mechanical, we have mechanical properties, optical, thermal, magnetic, or any other property, electrical property. So all these for a bulk material is depending upon first the structure, what structure the material is being made of, whether they are being made of FCC in the nature, or BCC in the nature, or hexagonal HCP in the nature. So first is based on the structure of the object. Then it should be defect free. It should not have any defect. So these are the two main consideration that we are going to give it for a bulk material to have better or good properties. Whereas for the nano-sized material, it depends upon the size of the particle, right? Whether it is 1 nanometer in the size, or 100 nanometer, or 1000 nanometer in the size. Next, whether it is 1 dimension, 2 dimension, or 3 dimension, or 0 dimension. Shape. And next, the surface area to volume ratio. This is the most important characteristics of any nanomaterial, is the surface area to volume ratio. Okay, so these three things, that is size, shape, surface area, and surface area to volume ratio, will provide, that is, each material will provide different combinations, will provide the different properties, whereas almost the bulk material properties are almost stabilized, because on the bulk materials are very long date backs, whereas these nanomaterials, so based on the different sizes of its uses and different shapes, right, the properties are totally different, or we can able to tell they give some novel properties, novel and interesting properties they can deliver. Okay, so that a thorough understanding of this nano level materials are very essential. So whenever you are going to work it on a nano sized material. Okay, so these three things attributed towards the properties, whether it is mechanical, electrical property, optical property, thermal or magnetic properties, okay, or electromagnetic shielding properties. So these nanomaterials, depending on these three factors: size, shape, surface area to volume ratios. Okay, so why the volume ratios or the surface area to volume ratio is important, right? So volume of the nanomaterial is generally given as surface area into thickness. So if I want to increase the, for a same volume, right, if I want to increase the surface area, the reason why I want to increase the surface area is, so on the surface I can have more number of atoms. Okay, so if I will increase the surface area of a film, which is nano in the size, I can have more atoms over the surface. So this takes up the mechanical load, right? Or this will act as a barrier for the fracture to propagate, or they provide the better gas carrier property, or it will reduce the magnetic property, etc., etc. So one is, so for a given volume, right, if I want to increase the surface area, so I have to reduce the thickness. So by reducing the thickness, I can able to increase the surface area of a nano-sized material, so that I can have more number of atoms on the surface. So that gives the extraordinary properties. Or whatever, sometime we may cut off one property, but whereas it will give better in both the directions. Okay, so such kind of analysis are required, especially for when we are going into the nanoparticle. Right. Again, there are different ways in which the nanoparticles will be termed. Okay, the first one is called as Nano Cluster. So, which is nothing but a collection of minimum of 50 units of nanomaterials. Then we called it as a Nano Cluster. Okay, a collection of about 50 units of atoms. So, which second is nanocolloids. So, which is nothing but a stable liquid phase which contains a part. In the particles will be collide and they form something an aggregate. Okay, these liquid particle are the liquid phases nanomaterials were collide among themselves and they form a aggregate. So, they are called as nanocolloids. And then third one is nanoparticles. So, nanoparticles are nothing but a solid particle. So, especially it is in the range of 1 to 100 nanometer. Okay. So, they could be either nanocrystalline or it may be aggregate or it may be a single crystal in the nature. Okay. So, the nanocolloids are in the range of 1 to 1000 nanometer, whereas nanoparticle, so it will be in the range of 1 to 100 nanometer range. Again, they may be either non-crystalline or a crystalline in the nature. Nanocrystal, that is a single one, a solid particle in nano range with single crystals are called as nanocrystals. So these are the various terminologies which we will come across when we are going on for a nanomaterial. Nanocluster, nanocolloids, nanoparticles and nanocrystals. Next, nano is newer to us, right? So nano is not new. So because these nanoparticles, especially the carbon black, what we are going to use it in our tires, right? So along with the rubber, the carbon black, which is of nano-sized particles, which are being used in the for making of tires, okay, which is started since late 1900. That is why most of the tires are black in colors. Okay, because of the use of carbon black as an additive material, so which binds with the rubber particle, which is usually white in color. When we are going to extract the rubber from the tree, so they will be white in the colors. So these carbon black nanoparticles, which have been added the rubber, natural rubber, so that the tires which are being of black in colors, and almost some of the smaller sized nano gold or nano silver particles are being also used, and even the milk, right, what we are drinking, which contain nano sized particle called as casein, a protein in the form of nanometers. Okay, and sugar, what we are going to use, so usually a single crystal of sugar will be 1 nanometer in the diameter. And yes, of course, our bones, so which are made of many nanomaterials. And the most commonly available carbon black can be extracted by burning a copper vessel. Okay, a copper vessel or copper thing, if you are going to burn, so at the bottom we are going to get a black shape or black colored particles. So if we extract those black particles, so which are, when we are going to see it in the microscope, they are nothing but of nanometer sized nanoparticles. So which are nothing but the carbon black. Okay. So when we are going to heat up, a copper plate, right? So the soot which forms at the bottom of the plate, when we are viewed these soot under a microscope, so they will be in the order of nanometers. So which are nothing but the easiest way in which the nanoparticles or carbon nano black can be extracted. And yes, so widely used, these nanomaterials are in the cosmetic products. Okay. The engineering products, nanomaterials are widely being used in the cosmetic products. Okay. The kajal worn by the ladies, right? So which are nothing but the extracted, contains the carbon black in the nano levels. Okay. And generally how they have been produced, why we are using it, and it is not new, then how we are going to manufacture it. Okay. So basically they will be manufactured either by the ex situ process or in situ process. Okay. In the ex situ process, they may be done by the physical way or by chemical route. Right? The nanoparticles can be prepared either by the physical method or mechanical method, like ball milling, CVD, chemical vapor depositions, right? Sputtering, or some of the physical way by which the nanoparticles. Similarly, by chemical, sol gel process is widely used. Chemical process of extracting the nanomaterials. So when we have to go for ex situ process, once if we are going to produce in a bulk, okay, right? The need is large, or we are going in for a mass production, then you can go for ex situ production. Next, I want the reproducibility. Okay, so whenever we are going on for a nanomaterials, so all the nanomaterials will not be of same size. Okay, so the particles sizes will be distributed. If you have taken some 1 gram of the nanoparticle, in that itself, right, all the particles will not be of 100 nanometers or meters. So it will be in the range. Okay, the range may be from 50 to 150 nanometers. Okay, so this nanometer level reproducibility is very much important, especially for bulk producing. Then stability of the properties are of concern, and I want to produce at lesser cost, right? When these 4 things are of consider, then you can go for ex situ method. Otherwise, you can go with the in situ method. So again, it also has a benefit, a single step by which you can able to produce the method. And yes, so when we are going for the bulk production, we have a problem of agglomeration. Okay, agglomeration of the nanoparticle may occur, whereas that is completely avoided in the in situ process. Since you are going to very lower level and also at a controlled atmosphere, the stability of the properties, stability of the nanomaterial properties are very high when compared with the ex situ, and they provide better interfacial interaction. Okay, so that your property will be improved. Okay, so based on the needs, whether we are going in for the ex situ method or in situ process of preparing the nano material. Okay, next, so composites we are going to make, right? So the material which have 2 or more distinct phase, either physically or chemically, then we call it as a composite. Usually this composite may be of macro scale, and if any one of the reinforcement or any dispersed phase, right, is smaller or lesser than 100 nanometers, then we call it as a polymer nanocomposite. Okay, because the composite we will have 2 or more distinct phases, both in physical as well as in the chemical form. So of which if any one of the phase or any one of this will be of nanometer in the size, then we can able to call that as a polymer nanocomposite. Okay, then how these polymers are generally classified? So as you know, they are generally classified into thermoset and thermoplastics. Again, this thermoset, which can be once if you have melted and molded it, then you cannot able to remold, because they have been formed by the strong bonds, covalent bonds. So it is very to break those bonds once it get settled. That is why the thermoset are having very higher strength, right? Because the bonding between the atoms are very strong, so they cannot be remolded. Okay, and some of the examples like you'll have polyester, then you'll have epoxy, formaldehyde, or some of the vinyl esters, or some of the examples for thermoset. Their bonding between the atomic bondings are very strong, so that cannot be broken up once if it is settled or if it is molded. Whereas in the other hand, the thermoplastic, so the atoms or the molecules have been formed by weak bonds, or we can call those bonds as weak van der Waals bonds. Bonds. Thermoplastics are bonded with weak van der Waals bond. Okay, so they are easily can be, the bonding between the atoms can be easily broken when we are going to reheat it. Okay, so they can be melted even after formulated. Again, they may be amorphous in the nature or they may be crystalline in the nature. Okay, so the amorphous nature are PVC, polystyrene, polycarbonate, ABS, are some of the examples for amorphous, and polyethylene, PET, polypropylene, polyamide nylon, POM are some of the examples for structured or crystalled nature. Okay, so thermosets, why they cannot be? So they have the strong covalent bond, whereas the covalent bonds are very strong, whereas thermoset, the bonds are weaker. Okay, so they have been with weak van der Waals bond. So when on reheating, so they can easily break the chain and we can able to remold it. Okay, and what are nanocomposites? So the maximum, the composites are in which you will have a nano in either in the volume ratio or in the weight fraction. So you can have, you will be in the range of 0.5 to 5% only. Okay, so the maximum order as per the literatures which are available, so you can able to alter the properties, right? So to a maximum of 5% weight or volume ratio. So what will happen afterwards or after behind that? So they will form the more agglomerates. For more agglomeration, or they will be collide at a single place instead of uniform dispersion of this nanomaterial. They will be accumulated in a single place, so that we cannot able to get the uniform strength throughout the material. So because of these reasons, these nanomaterials are usually added in the range of 0.5 to 5%, either weight or volume. Right, then how these nanofillers are being classified? So basically they are being classified as organic and inorganic materials. The organic materials are nothing but nanofibers or viscous in the nature, and they are classified as they are nothing but chitin, starch, cellulose and chitosan. So those are the organic type of nanofillers which are added with the polymers. Again, or so they may be a nanoclay or it may be a metallic nanoparticles. Okay, inorganic may be either a nanoclay or it may be metallic nanoparticles. Again, the nanoclays are different varieties of nanoclays are available. So they are bentonite, hectorite, cavolite, saponite, morlite. So these are some of the nanoclays which are commercially available. Whereas the nanoparticles which are metal, so gold, silver, silica, copper, zinc oxide, copper oxide, titanium oxide, etc., silicon carbide. Okay, so are some of the metallic inorganic nanoparticles which are available. Then, and this is nothing but a figure of single walled carbon nanotube. So single walled carbon nanotube, right? So we are having only carbon, so which has been rounded in the form of a rod. Okay, whereas here, if you are seeing it, so it has multiple level of carbon nanotube. So we called it as multi-walled carbon nanotube. So if these carbon tubes are right, instead of circular in the shape, if we are opened it, right, they form a two-dimensional pattern like this, something like this. Okay, then we called graphite or graphene, or we called it as a graphene. A two-dimensional carbon is what we will call it as a graphene, a single wall carbon nanotube, or you can have a multi-wall carbon nanotube. And also, if this was in a two-dimensional, then we called it as a carbon. So this is one difference, and another difference is, so here in the carbon nanotube, the carbon percentage will be from 90 to 95% of will be having carbon, whereas in the graphene, so it will be something in the order of 99% of carbon. Okay, so that is why the graphene is also called as a wonder material. Okay, so the 99% of the carbon is called as, or what we will call it as a graphene. Next is about the clay, right? So when the clay, right, so they may be arranged either horizontally, parallelly, or 90-degree, or it may also be inclined, right, in a particular layer by layer, right? So all these layers will be parallel. When they will be mixed with the polymers, when they will be added with the polymers, okay, so the polymers may form the around the layer or silica. Okay, if the polymers form around the layers of silica, then we call, then it is nothing but a phase separated microcomposite. Okay, so polymers around the layer of polymers will be placed around the layer of silica, then we called it as a microcomposite. Suppose if the polymers are moved in between the layers, okay, in between the layer, then we are going to call it as intercalated composite, and they are nano in nature. Okay, so in between each layer of silicate, if polymer occupies the space, so if this is the nanoparticle, and around the nanoparticle, if we have a polymer around it, then we call it as intercalated. So again, they will be arranged in a series, a particular fashion. Okay, they will be arranged in a particular fashion only. Next is the recent one, which is called as exfoliated nanocomposite, in which this layer of silicate will not be arranged in a regular pattern. Okay, this layer of silicate will not be arranged in a layered pattern. Then we call it as exfoliated nanocomposite. Okay, so if a layer, an entire complete layer of silica has been surrounded by a polymer, then we call it as a phase separated microcomposite. If each layer are surrounded by the polymers, then we call it as intercalated nanocomposite, and if this silicate does not form any pattern, right, and if they have been surrounded by the polymers, then we called it as a exfoliated nanocomposite. Okay, right. Why we are going in for nano? So because of better mechanical properties, like it may be a strength, modulus, or better dimensional stability. Dimensional stability of the material is also important, right? Because when the material has been exposed to different environment, the dimensions of the product for which you have made should not deviate. Okay, so it should not deviate because of the environment, right? You can use the material at a 40-degree temperature, or you can use the material at 60-degree temperature, or you can use it at minus 10-degree temperature, right? So under these conditions, it should not vary its dimension, or the dimension should be stable. Okay, and the next reason is, so it decreases the permeability of gases, water, and hydrocarbons. Okay, so these properties are very much important, especially if you are going to make the biofilms. Okay, if we are going to make the biofilms or packaging materials, then this gas barrier properties are very much important, because when you have any material, packed a material, right? Suppose if it exposes to the oxygen or atmosphere, right? It should not permit the oxygen to pass into the packed material, right? Or for example, we will have a biscuit packet, right? We will have a biscuit packet. So if this packet or the wrapper which is around the biscuits, right, because they will be kept at a different atmosphere, right? Usually in the usually at room temperature, again the room temperature may vary, that will not permit the oxygen or any other gases to go inside the biscuit, right? If it goes inside the biscuit, what will happen to the eatables? So they will become or loses its crispy property, right? Any packed, right? It may be a Lays, right? It may be a kurkure packets, anything, right? So they have these barrier properties.
Sir, yeah. Hello, sir, are you here? Hello,
Sorry?
Yes.
Yeah, sorry. There will be a network problem. Okay, I think now it's okay, I think.
Okay, you can continue.
Yeah. So the another important property we are mostly we are not considering when we are doing the research is the flame retardancy and smoke emission. So we are telling that we are using the polymer composite for applications, right? So these automobile application may come across fire accidents, right? You can make any dashboard or headrest or something in the automobile, or you can make a chair, right, for a passenger to sit in a railway station or something, right, or inside the cabin of a train, etc., where they may also have exposed to the fire accident. Okay, so this flame retardancy is also very important for this kind of automotive application. When we are telling that this particle can be used or this material can be used for the automotive application, this flame retardancy is also very much important. And sometimes these glass fiber are widely used as a cylinder tank for carrying the chemicals or is being made, right? And next, so for the better appearance, right? So for the better appearance, then it may have a better electrical conductivity, sometimes the optical clarity, right? Sometimes even nowadays the specs what we are wearing, right? So the glass specs have been replaced with the polymer glasses, and they will tell that it cannot be broken even if you have dropped to the ground. Similarly, the holder for the specs or glasses, so all are being converted from the conventional metal to a lightweight polymers, right? So at the same time, when we are going to use it for a specs, a polymer for the specs, and they will tell that it is scratch free, then smudge free, fog free, right, etc., etc. So all these can be improved or can be incorporated, right, using these nano materials. Okay. So how they will improve? Suppose if for a case, if I will take a microparticles, okay, microparticles I have filled with a resin, right? Here, if I will see for a square, right? So we will have 1, 2, 3, 4, 5. So 6 number of microparticles are available. If the same area, if I will filled with a nanoparticles, I will have more than this, right? I am having more amount of nano fillers I can able to provide. So what will happen? So I have more area, surface area I will get. So as I am getting the more amount of area, the material can able to withstand higher strength, or it will have higher stiffness, right? So those properties can be improved. This is how the nano fillers are, even at a very low filler percentage of 2%, 3%, provide better mechanical property or thermal properties, is because it occupies more amount of fillers in a given area when compared with the micro filler. So these atoms will take up the more amount of loads. Okay, so they have a larger surface area, and also the interface between the nanomaterial and the bulk polymer are excellent when compared with the micro filled particles. Next is, so here if you have seen, when I am going to add the nanoparticle in a from 0.1 to 10%, right? So as I am adding up the nanoparticle, the strain to failure increases, right? So strain to failure got to increases, and up to here something around 6 or 7% it reduces, right? So what will happen when the strain to failure is increasing, right, or the strain is increasing, which means it is taking up more load. The physical meaning, when the strain percentage of strain to failure increases, is nothing but it has more strength bearing capability or capacity. Okay, so this strain to failure can also be a reason right? Increased strain to failure can is also a reason for in the properties of our mechanical properties. Mostly we will discuss with the tensile strength, tensile modulus, flexural strength, flexural modulus. You can also discuss with the strain to failure, okay, as a evidence, right? Because we always want to know why this at 10 percentage of volume ratio or weight percentage, my material is lower property, whereas at 20 percentage my properties are improved. The reason behind, one of the reason behind is the strain to failure will also increases. Okay, strain to failure will also increases, that increases the strength again. So we have FR, right? E is equal to, right? By the Hooke's law, we will have within it is directly proportional to a elastic constant called as Young's modulus E, right? So you can discuss this. So what will happen if my strain increases, right? The modulus decreases, right? For a same amount of stress, if my strain to failure increases, then the modulus decreases, right? So these are some of the cross checkings that as a researcher we can have to carry out. So modulus decreases, but strength increases. Okay. Next, so we tell that it improves the fracture toughness. How does it will improve the fracture toughness? These nanoparticles will divert the crack propagation. Suppose if this is a crack propagation over a surface, okay. So if there are no materials, so what will happen? It will move in this forward direction and break, right? So if I will have some micro or nano sized particle, so it will deflect, right? It will deflect the crack, right? So what will happen as it deflect the crack, the area of crack propagation or the time take for the material to failure will increases. So thereby you can able to increase the lifespan of the material. So it, right, it deflect or bridges the crack. This is deflecting the crack. Thereby I can able to increase the fracture toughness of the material. Okay, it is deflecting. It deflects the crack here, so that it form. So it will go at a different pattern, right? Or it may improve the time to reach the failure. Next one is it bridges the crack, right? Here it is deflecting the crack. The next is it is bridges the crack, right? It is just like when we have a that is, we are making stitches, right? It is stitching the crack. So as it stitches the crack, right? So it this nanoparticle will take the load, right? So thereby it also improves the fracture toughness, either by deflecting the crack or it bridging the crack. Okay, thereby it absorbs the more energy, so that the time taken for the crack, right, to reach the material end surface or complete failure of the material to occur takes longer time. So these nanomaterial crack, okay, so it absorbs and dissipates the energy, right? So it reduces the crack propagation speed. Next is conductive, that is a gas barrier property, is what we have told earlier, right? As when they have these nanomaterials have been arranged, right, in a random fashion, just like the crack to propagate in a single phase, right? These gases will reaches from the initial path to the final path. It take a longer time. Okay, so thereby I can able to improve the electrical conductivity, or similarly I can able to Here one of this is the particle should not be uniform. Dispersion of the particle is not required for this case of for the case of electrical conductivity. Next one is nothing but called as a gas barrier property. Right, so since they have been arranged in the non-uniform pattern, so it follows a different path to reaches the exit. Okay, so thereby it reduces the gas barrier property, or it reduces the particle losses. Next is flame retardant or flammability property. So how does this nanoparticle enhances the flame property? So as you are going to burn, right, this layer, right, this layer will burn initially and they will deposit a char. Okay, so these initial layers depositing to the flame or heat, right? So they will deposit the char over the another. So this char, okay, or this dirt particle or this particles, right, broken particle act as a barrier for the flame to reach from the initial position to the final position. Okay, this unburnt polymer act as a barrier, right? So thereby I can able to improve the flame retardancy or fire performance. In otherwise, it's called fire performance of the material, right? So they form a char type of layer, right? So they form a char type of layer and thereby it restrict the flow of heat, okay, to the unburnt. So thereby it enhances the performance, fire performance of the material. Okay, so we have seen different things which has which produces the nanomaterials, right? Then how we can able to manufacture the polymer based nanomaterials. Okay, so first one is the in situ polymerization, so in which the polymer and the monomer solution are mixed. Okay, the nanofiller and the the monomer and the nanofillers have been mixed and they will be kept out for some duration of the period so that the polymerization of the material will occur and the solvent will burn, right? And once the solvent get evaporated, we are in a mold, three-dimensional nanocomposite. This is the simplest method in which the nano polymer composites can be prepared. So you'll have a monomer solution and in which you are going to disperse the nanomaterial and allow the polymerization to occur, and once the solvents get evaporated, pour it into the mold. Okay, and the second one is, so you will have a especially graphite, right? So you will have a graphite sheets and which will be mixed with the polymer, and these polymers will form the inter between layers, right? And then polymerization, when it is being exposed to some temperature, so polymerization will occur and they form a graphene or nanographene polymer sheets. And the next is the solution blending, right? So in which you will have a mechanical stirrer, both the polymer resin as well as the nanomaterial will be based on the volume fraction or weight fraction calculation. So you are going to pour it and stir mechanically or manually, right, for a given speed and for a given different durations, and then allow it to settle. So the polymer will form a material around the nano and they will be further poured into the mold depending on your requirement. Next, this is what we have seen earlier. That is the layered nano clay. So mixed with a polymer solution, either in the form of a ultrasonic bath or mechanical stirrer or manual stirrer, and then allow it to settle down for some duration of the time. Then they form a nano clay composite. And the next one, so you are going to use it the chemical method. So you are going to have a nano clay or a cellulose fibers and the nano clay. So they will be mixed in a funnel, and they will be dropped, and a biofilm will be formed, and this biofilm or the moisture in the biofilm will be pressed and taken out, and these type of films will be constantly placed and pressed at a constant pressure of around for 2 hours, right? So that a nano clay based films or nano clay reinforced cellulose nanofibril can be formed. Then melt blending. So melt blending, so as you know, we are going to shear the nano material. So as the shearing will take place, the particle sizes will be reduced, right? So as the reduction in the particle sizes take place, and then they will be added with the polymer, and then the polymer nano composite will form. Melt blending. And the next one is the extrusion process, where the polymer, especially the thermoplastics and graphene or any nano materials, so they will be poured in a single extruder, or it may be a double extruder. So they will be melted to a preheating temperature, and then as the screw is being rotated, so they will be okay at the heated part, and they will be extruded with a, and here we will have an die. So through the die we can able to take this out and then cool it for a particular time, so that they will form a sheet or a 3-dimensional nano material. Okay, and then once if you have made, so we need to characterize it. Okay, so especially the first you need to characterize the nano materials. Okay, so either by wide angle X-ray or small scattering X-ray to know the crystal size or nanomaterial size, and then you can go with the TEM, AFM or SEM, right? So to analyze whether the uniform distribution of the material was taken place. Uniform distribution of the nano clay was achieved or not. And then you can, next you can go for the mechanical characterization like tensile test, tensile, compression, flexural, as per the either ASTM method, or you can go with the ISO, or you can go with the European committee, right? Based on any one of the standard has to be followed. Okay, or other than that we will also have some other standard, so which are driven only for those companies like Boeing specification test, suppliers of advanced composite material association test. Then we will have composite research advisory group, then European construction material for aerospace application. So these are company specific standards, but most widely used are either ASTM or ISO standards. And these are various standards which are available for finding out the resin content, fiber content, void content, etc. Then tensile test, compression test, in-plane shear stress. Then you can have interlaminar shear stress, then flexural stress, and there are different standards. Okay, and for thermal analysis, and also to analyze if there will be any chemical changes occurred. Okay, so you are going off for FTIR, Fourier transform infrared spectroscopy, or you can also go with the Raman spectroscopy. Then you can go with the differential scanning calorimeter, to analyze, right? So the weight residue, and then you can go with the dynamic mechanical analysis to know how the storage modulus, loss modulus, and loss factor of a material, how the temperature and frequency affect the storage modulus, loss modulus, and loss factor. Okay, that is what has been given here. A general TGA analysis test will give us, right? So as you are going to heat at a different temperature, so how much the weight has been retained, right? So till at least something around here, right? So something around 350 degree, I can able to retain something 85% of my weight I can able to retain, right? So this layer is called volatile component, right, are being bonded. Next, the polymers are get bonded. Then finally, carbon black will be get burned off. Then the residue or ashes will be left out. A typical thermogravimetric analysis curve. Similarly, we will have a DMA curve. So the green color shows the how the temperature affects the storage modulus, or in otherwise how the absorption capability of the material, energy absorption capability of the material get affected with temperature. And this red color, right? So red color will shows the loss modulus. So loss modulus is nothing but energy dissipation. How much energy that has been released in the form of a heat by the material. How they are being get affected, and this green color, okay, will give the tan delta. The tan delta is nothing but will give the peak of the tan delta will provide us what we will call it as the glass transition temperature, the temperature at which the material polymer begins to soften. Okay, and also it provide how much amount of the damping or the loss factor has occurred. Okay, so here this is they have done it from -100 degree to 150 degree centigrades. Okay, so the value is depending upon the applications. The temperature is depending upon the application in which, so that up to what temperature I can able to use the material without any loss in my storage capability, that I can able to analyze it. Now let us comes into it. Nano clay. So natural fibers. So basically they have based on whether they are being extracted from the plant, animal, or mineral. They have been classified based on these three, and especially the plant fibers, they are also called as cellulose fiber or lignocellulose fibers. So based on the extraction, whether they are extracted from the stem or bast, leaf, seed, fruit, wood, stalk, or grass, right? They have been extracted from any part of the plant. And these, it may be either a jute, banana, or leaf, sisal, abaca, pineapple leaf fiber, then seed, cotton is a best example. From the fruit, we will have coir, oil palm, then sponge gourd, then grass, so corn, bacassi, bamboo, or the varieties of grasses from which the natural fibers, plant fibers are extracted. Why we are going in this work for jute fibers, right? A comparative study of various properties like density, length, diameter, the strain to break, right? Tensile strength, right? So the jute, especially in our country, jute is the topmost fiber which is available next to cotton. Okay, so jute fibers are widely available, and also when compared with either a sisal or coir or banana, right, you can have a constant cross section of the fiber can be achieved in the jute, because the extraction of the jute process was completely mechanized. When compared with the other fiber extractions, they will be manual. Okay, whereas these cotton and jute fiber extraction and processing techniques are done to a complete to an 100% mechanized or automized way. So I can able to get the even properties. Okay, these are some of the literatures. Okay, but the moisture content is very high. Okay, moisture content is around 12%. But if you have compared the specific strength, right? Specific strength is nothing but the strength divided by the density, right? So it is having around 140, it ranges from 140 to 320. Whereas if you have compared, right, it with some other like sisal, it ranges from 55. Whereas bamboo it is a little bit higher. Okay, 383. Okay, pineapple leaf is 187, but it goes up to 1130. Okay, so these variations in the properties, right, is always attributed towards the property of the final composite, because the place in which the natural fiber cultivated and the way in which we are extracting are totally provides the these properties. Okay, and the natural fibers are most widely used, especially as a secondary structural member, not a primary structural member, because of moisture, and also they are having a low load carrying capacity. Okay, so these are being used as a raw fiber, as insulating material, yarn as a fabric, okay, knitted goods, and with the help of fleece, felt, they are used as insulation material, thermal insulation purpose, soundproofing or sound absorption material, etc. Okay, and these are also being used as interior and exterior parts, decking, tableware, office equipments, containers, etc. Nano clay. So since we are dealing it out with the nano clay material, right? So this is a Montmorillonite MMT nano clay. Okay, what we are using it in our in this work. Okay, so again this nano clay may be either tetrahedral or octahedral in the nature, right? And thickness will be about 1 nanometer and about 50 to 150 in one of its direction, right? So why nano clay? So right, the automotive component packaging material, right, the nano clay, the usage is continuously increasing. Okay, so the use of nano clay as the reinforcement in, especially in the automotive packaging, right, etc., are continuously growing is one. Second thing, they have been good market as they are being used widely. So these nano clays have very good market when compared with the either metal oxide based or CNT based, because the cost at which they are providing the properties are very high. Okay, so as seen earlier, so these are various kinds of nano clay which are available. So aluminum silicate is called kaolinite, calcium based is called Montmorillonite, and potassium based is called illite, chloride. So again, this chloride magnesium based or iron based, lithium based or nickel based. Okay, so here we have used the Montmorillonite, and these are the specifications of the material, and this is how a Montmorillonite will be prepared. And so here we have used it because of exfoliation. Okay, exfoliation is they can be arranged in the randomly manner, not in a layered silica, right? And so the objective of the work first is to predict the optimum parameter for uniform dispersion. Second, how the nanoclay loadings are affecting the property. And next, when if I am going to add it with the jute fiber, how does this nanoclay influences the property? Okay, so these are the main objective of the research. Okay, first I need to find out whether these nanoclay at different percentages are uniform or at what percentage I am getting the uniform dispersion. Next, right, and this is how the jute is being cultivated and harvested, right? So first the nanoclay was observed in the SEM with EDAX to show the material with the silica as the peak. Okay, the silica material with a peak value. So it confirms that it is made of silica as the maximum material. Second thing, so we used the ultrasonification process with a bath, right? So the process will be here, the capability of this ultrasonic is from 0 to 0 hertz. Okay, frequency in which we can operate is maximum to a 20 kilohertz, right? So I need to optimize the parameters. How much frequency I have to use, right? And how much will be the solvent or resting period or gelation period has to be done. Okay, so first we have done with the 100%, that is 20 kilohertz, and then for a duration of 30 minutes. Okay, this is the scene. So and from this, if you have seen, so as I am going to lift it out for the 30 minutes of duration, it forms the agglomerates. So I cannot able to use this for my preparation of this parameter. I cannot able to use. Okay, so I have varied for 30 minutes, 60 minutes, 90 minutes duration. Next, we have done with 50%. Again, here also we have done it with 30 minutes, 60 minutes, and 90 minutes. So here only for the optimum value. So optimum value or uniform dispersion, we found that it is still in the liquid form and also having dispersed. Nanoclay was dispersed. So next we have to analyze these materials, right? In naked eye we are telling that it is okay, but that is not enough. So we went into the AFM microscopy to show the AFM of 5.8 nanoclay percentage for 30 minutes, 60 minutes, and 90 minutes duration. Okay, so 5.8% for here 60 minutes. So we can see the large number of nanoclay. These white dots are nothing but the nanoclay, which are somewhat distributed. Whereas for 30 minutes, we are seeing only a few amount of nanoclay, and also nanoclays are mostly accumulated here. So similarly, when it goes for the 90 minutes, so some amount of accumulations are occurring here and all, right? Next, same images to dissipate the same, right? For 30 minutes, right? So we have very less number of nanoclay. So if we are seeing it for the 60 minutes, so a large number of nanoclays are occurring. And if it is for the 90 minutes, right? So the nanoclays are get accumulated or colloidal, nanocolloids are taking place. So I can able to tell, or we can conclude that 5.8% of nanoclay with 50% amplitude, that is 10 kilohertz, and stirring for 60 minutes, uniformly distributed particles, right? Okay, so next with that I will add a different weight percentage of nanoclay, 1, 3, 5, and 7, and my optimum are 10 kilohertz and 60 minutes. Next, I will check it out right. So here we have used the hand layup method. So here we have used the vertical type of hand layup method, so that the air bubbles present will be of negligible, or no air bubbles will be presented when compared with the horizontal type. Okay, and also no need for roller to be used. Okay, so these are the various that is neat resin with 1%, 3%, 5 and 7% nano clays plate. And this is jute, right, with the jute fibers. Then this is 5% jute, 10% jute, 15%, 20, 25 and 38% of jute fibers plate. Next is the stencil specimens, tensile, flexural, impact, vibration testing specimens of all the products, right? Nano clay, neat resin as well as jute fibers. These are the various tests which are carried out, and these results, right? And a 3-point bending test, then to test the flexural strength of the material, and instron to test the flexural, and digital impact tester, and DMA equipment. Then we will have a free vibration tester, and next we will have a digital what do you call this, is a Wicker hardness test to test the hardness, and also the computer hardness testing machine to get the Young's modulus in the non-destructive way. Okay, so and then these are the test result. So as with the increase, right, 0% is nothing but the resin, polyester resin, and with the addition of 1%, a slight increase, right? Blue color indicates the flexural strength and green indicates flexural modulus. As with the addition, right, it slowly increases and then it starts to decreases with 7%. So I can tensile strength at 5 volume percentage, I am getting the maximum value. Next, similarly for the flexural, so it starts to increase slowly and reaches the maximum value and then it decreases. So here also I am getting at 5 volume percentage, and impact, the response will be very to failure is very high. Okay, next, so 5, since 5-8%, it provides the better tensile, flexural and the impact properties. So I will take this 5% weight of the composite as, sorry, nano clay as the better property, and this will be added with the jute fibers to produce hybrid composite. So by varying the jute fiber as 5, 10, 15, 20, 25, 30. So when my percentage is around 15 volume percentage with 5% of nano clay. Okay, so both are, sorry, here also volume percentage. So 5 volume percentage of the clay, I am getting better mechanical tensile strength. Whereas at 25 weight percentage of jute, right? So I can able to predict. So depending, so 5-8% at 15 weight percentage, I am going to get the better tensile strength and impact. Whereas at 25 weight percentage, I am getting better flexural properties. Okay, and the reason, right? So this is for the 3 weight nano percentage. So we can see the nano clays are very lesser. Okay, the distribution of the nano clay over a particular surfaces are very lesser. And whereas here for the 5-8%, so it was distributed throughout the surface, and hence they provide better mechanical strength or property. That is reason why 5-8 nano clay are better. Then with the, right, with the jute fiber and the nano clay, right? So here we can see the interface adhesions between the fiber and the matrix are very poor, along with the fibers have been not properly adhered with the matrix. So the strengths are low. Right here, if you have seen, so even after it is break, right, we are seeing the adhesion is very good. Okay, adhesion between the fiber and the matrix are very good, so that I am getting the better or best properties at 15 weight percentage. Okay, even right, the fibers have bent without failure. Not all the fibers have been failed. Next is, so as you know, the water absorption percentage. So decreasing. Okay, this is one good absorption. Whereas when I will add the jute fiber, right, it when compared with the 5-8 percentage, right, so it goes to sorry, it increases, sorry, decreases. And the next modal analysis or vibration analysis was carried out with free vibration test under FVT, free vibration test mode, and also we have compared it with the theoretical way. Okay, and this is a frequency response curve, and the table column shows that with the addition of clay, right? So with the addition of nano clay, the what do you call, the vibration, right, or the frequency increases in both mode 1 as well as in the mode 2, and this is the theoretical and this is the experimental one. So there will be a deviation, and this deviation may be due to the because hand layup method was followed. Next, we have done it with Fdir. Again, we have added it for the jute fiber. So again, so with the addition of jute fiber also, this continuously vibration is, or the vibration natural frequency continuously increases. Mode 1 as well as mode 2 frequency. Okay. Next one is the storage modulus, that is DMA. So how the storage modulus when compared with the neat resin, right? So this is neat resin, and with the addition of this nano clay, the storage modulus are increases, right? And if we compare at the different temperatures, right, we can able to find out the storage modulus of the material, which increases with the addition of with the addition of nano clay. Next, tan delta, which gives the glass transition temperature, that is peak. Peak of this gives the glass transition temperature, and also with the addition, there is a shift from the value, right? So there is always a shift in the value or the glass transition peak, or the peak has been, right? This peak got widened. These curves got widened up. So to summarize this, we have a table, right? So the glass transition temperature increases up to 25.8% of jute, whereas, right, at 30, right, it starts to decreases. Yes, of course, the difference. So if I will compare it with the polyester resin, the difference will be very higher, right? Next, in order to decrease the, we have done the chemical treatment, one with NaOH, KMNO4, and then a combination of this. So with this, I will conclude it, right? So this is NaOH treated fiber, that is 2.8% of NaOH and all the chemicals. Here also 2.8% of KMNO4, and here 1.8% of NaOH, 8% of KMNO4 was treated. Okay, and these fibers have been used for fabricating the plate, and again the various tests are conducted. And for untreated fiber, the tensile strength is 40.38, and NaOH it is 43, and with KMNO4 it is 44.68, and with the combination of these two, right, it was increased to 47.12. Okay, so the combined effect of NaOH and KMNO4 will provide us the better tensile strength. Similarly, the flexural, it was started with 166 and increased to 201 megapascal. And for impact strength, started with 151 and moves to 172. Okay, and in order to, right, so we have to do the FTIR analysis, and from the FTIR analysis, the transmittance and wave number. So we are finding out the different peaks at different wave numbers. So each wave numbers corresponds to a particular relationship. What has happened, right? Whether the OH bonding was removed, right? Or the bonding between the carbon and the carbon is broken or not, okay, was carried out. And let me go to the conclusion very quicker. Okay, right. So 50%, that is 10 kilohertz, and for a unit 60 minutes, we got the optimum dispersion time. First, and better properties are achieved at 58% of nanoclay, and then we have was achieved with 58% of nanoclay with 15 weight percentage of what do you call jute fibers. Okay, and this is one of the PhD work of Mr. Arul Murugan, and got published in four papers. So my acknowledgement to his work. And these are the list of publications and references, and any queries. And now we can spend some time for queries.
Thank you, sir. Thank you very much for the wonderful session, sir. I now may request the participants to post your queries.
Yeah.
Either you can unmute your mic and you can direct it up to the professor, or else you can drop the queries in the chat box. So I think already we have a few questions in the chat box from Mr. Nataraj MB. Mr. Nataraj, are you here? Mr. Nataraj? Okay, sir. I'll read it out for you, sir.
Yeah. Thank you.
On what basis the weight percent of polymers to be selected before mixing nanoparticles? This is one question.
Okay, so actually we have to do, so there is no hard and fast rules. So the nanoclay percentage will vary. So maximum, as we got in this work, as well as from the earlier literature, right? We can have a maximum of, we can go for maximum for 58% of nanoclay. Okay, whereas this variation, right, here also I can get increase, first it is increasing, and then it goes down at 7. I don't know again the value at 6. Okay, at 6 also it may increases. Okay, so again that is also one of the what can also be done as the future. What will happen between 5 and 6, whether they increases or decreases. Okay, again here we have taken as 1, 3, 5 as a odd number, even because as you are going to increases, right, the deviation on the values are not very higher, right? Even you can go with 1%, 2%, 3%, 4%, 5%, like that also you can go. But here the differences between 1% and 3% is not very high. The will have some 4 to 5% variation in the strength was obtained. Okay. Yeah. Next, any other questions?
Yes, sir. What are the sample preparation things need to be followed for TEM characterization?
For?
What are the sample preparation things need to be followed for TEM characterization? TEM.
Okay, TEM. Yeah, TEM is here again because it is polymer, right? So suppose if it is a polymer material, we need to gold coat it. So again, the resolutions you need Similarly, then how much you want to zoom it, zoom or magnification factor, right? So again, those are depending upon the equipment or the equipment specifications. It's totally depending upon the specification. We can have in a low magnification, medium and higher magnification. So since it is polymer, so they will definitely coat with gold coating, or sometimes they will do it with silver sputtering or silver coating will be done. So where you want to do the analysis, whether I want to do the fractured part, I want to know how the fracture is occurred, then you have to cut the fractured part. Or I want to do the TEM analysis to see the distribution of my nanoparticles, right? So you can take up on the surface, right? So depending upon your need, I want to study the fracture, how the fracture is going to occur, then you cut the fractured portion. It may be either tensile fractured specimen or flexural. I want to study the surface. Yeah, yes.
Yes, sir. And one more question, sir.
Yeah, yes.
So you talked about the water absorption test.
Yeah, yes.
In that, you have shown the variation of the mechanical properties with respect to the time exposed to the water.
Yes.
Now, what are the methods that you follow for water absorption? So instead, whether you immerse the specimen in the liquid or water, or you keep it in a chamber to.
Yeah, yes. Here we have used, we have immersed it in the distilled water. The water absorption also can be done on that is distilled water. You can also do it on what you call different sea water, right? Different environment depending upon the environment, or you can keep it at freezer, right? Freezer for some timing, or you can have it in a AC environment, right, where you can have a 16-degree or 20-degree temperature. So here we have done it with the distilled water. We have immersed the samples in a distilled water and then taken out every day, each day. So each day we have noted down the change in the volume, change in the weight. Okay, change in the weight was carried out, and with that the percentage of moisture absorption was calculated. So here 24 hours time was done. Each day we measure the weight and till there will be some saturation level. Okay, that is the difference in the value between some 2 or 3 days will be almost of same value. Then we tell that as a saturated moisture absorption percentage. After that, it won't absorb moisture, or the moisture absorption will be very, very negligible. So till that time, we have to do the moisture absorption.
I think, yes, thank you, sir. Thank you so much, sir. Is there any other questions from the participant side? You may
Yes. This is Dr. Piyush from Hindustan University. I want to ask a question, sir. Sir,
Yes,
it is
sir.
a very, very nice work. Nice to see such a good work. I
Thank
just
you.
wanted to, just out of curiosity, there is one mind. I have seen a lot of studies on nano clay.
Yeah.
So I just want to ask you, what is the main purpose of choosing only nano clay? Like you could have worked with other nanofillers also, like graphene, maybe bismuth carbide, carbon nanotubes, and all. So what is the main reason of going with nano, except cost and all?
Yeah. Here I am going to use it in the natural fibers. Okay. So I want to improve the property of the natural fibers. So these natural fibers are especially used it in the secondary part, or secondary structural member, or interior part of an any automotive or any cases, mobile cases, or other things, where since already the natural fibers are used only for the low end application, I cannot use the higher value. So carbon nanotube and all, whatever you have said. So those will be of, again, the cost will be okay. So since these nanoclays or natural fibers are used only for a low end application where the cost is a significant factor. Because
Sir,
of this reason, yeah.
yeah, I absolutely agree with your viewpoint, but in this one, if we talk about the internal members, like for example, if we look at into the dashboard of a car or maybe
Yes.
dashboard of the of the aeroplane and all,
Or anything,
so
yeah.
all these type of interior components, what I have seen, they are oftenly subjected to some sort of vibrations in form of a
Yes.
cyclic loading.
Yes, yes.
So just want to ask if you have done any fatigue studies on the nano clay based natural composite materials and all, because to my understanding, I think this nano clay based natural fibers may have poor fatigue properties even if you mix nano clay also. So
Definitely, definitely.
you have any studies supporting this statement, or have you investigated the fatigue life
Yeah,
prediction
no,
also?
no, actually, we have not conducted any fatigue test. Actually, the scholar is now currently doing it as an extension of his PhD work. Currently, he is doing it on the fatigue study of this nanoclay. It is on process.
Okay, one suggestion I would like to add
Yes,
up here.
please.
See, all these in-service components are not only subjected to dynamic loading,
Yes,
they are actually subjected to a mixed mode loading. Like for example, you can have static loading at one instant and the other instant it could be dynamic, or
yes,
you can
yes,
have a mixture of static plus dynamic.
yes.
So what I suggest, if you are looking for an extension for this fatigue work, I suggest you please also try to investigate the fatigue behavior in a combination of static plus dynamic loading. I think that will be more suitable for this internal, that will be more suitable for designing of this internal components member actually. This is
Yeah,
the
yeah.
issue that I have faced. I am just telling you out of my experience. So please try to investigate this combination of static loading plus dynamic loading. That
Dynamic.
will be the more realistic prediction, sir.
Yeah, sure.
Anyway,
Thank
sir,
you.
thank you. This was really an informative session. I
Thank you.
really have gained new insights into it, and I wish you all the best for
Thank
this.
you. Yeah. Thank you. Thank you for your suggestions. We will definitely take up this issue also. Yeah. Thank
Yeah,
you
in
for the
case
new
you
insight.
need my help, you are more than welcome to contact me also, sir.
Sure, sure. Definitely. Yeah.
Thank you, sir.
Yes, sir. Yeah. Thank
Yeah.
you.
Thank you, sir. Any more questions from the participant side? And I would like to welcome our former head of the department, Adak sir, here for the FDP. We welcome you, sir. Any more queries from the participant side? Please kindly post the queries in the chat box, or else you can unmute your mic.
Yeah.
I think that's it from the participant, sir.
Yeah. Okay.
Thank you, sir. On behalf of the Department of Aeronautical Engineering, I would like to convey my sincere thanks and gratitude for you being here, accepting our invitation, and giving this wonderful presentation for all the participants all over the country as well as overseas. So I hope that a lot of people have learned more, more techniques, and the session was really informative, and hope they have enjoyed it. So thank you for being here, sir. It was a nice presentation, and it's a pleasure having you here as a resource person.
Yeah. Oh God, because as more and more number of questions, we will also get insight into the work, newer work. Okay. Thank you.
Thank you, sir. Thank you so much. And I now may request the participants to give your overall feedback in this session. The validity session is about to begin. And anyone, please, we have many participants over here. Please kindly share your entire feedback of the overall feedback of this entire FDP program, about the organizing, about the speaker's presentation, and the overall takeaway from this FDP. Kindly, anyone, please, one by one, kindly share your experience. This will help us to improve our, the the organizing way for our upcoming programs also. The feedbacks are most welcome. The session is open for the participants. Kindly unmute your mic and share your feedback. Thank you. Yes, sir. Go ahead.
So am I audible?
Yes, sir. You're audible, sir. Kindly introduce yourself and share your feedback, please.
I'm Dr. Kumaran from SRM University, from Mechanical Engineering Department.
Hello, sir. Hello.
I first thank the organizer for aptly choosing the resource persons and for appropriately communicating all the participants, the events in the WhatsApp group as well. It was really a very interesting. All the expert speakers were delivering a very good lecture. And some of the lectures were also inspiring, including the last one. And all the participants were also interacting very much. So that's also very interesting to listen. So I thank the organizer once again, as well as the resource persons, including Dr. Venkateswaran. He's one of my former colleagues. Okay, thank you. Thank you all the participants also.
Thank you, Kumaran sir.
Yes, sir.
Thank you, sir. Thank you, sir. Thank you for your feedback. So, any other feedbacks, please?
Hello.
Yeah, please.
Sir, good evening, sir. Good evening to all.
Good evening, sir. Please introduce yourself.
Yes, sir. Myself, Saravanan, Assistant Professor of Mechanical Department, working in K. Ramakrishnan College of Technology. And so before going to give the view of this FDP, so I would like to share one thing that I am an alumni of K. Hindustan College of Engineering and Technology. And now I am an additional COE at K. Ramakrishnan College of Technology. It's an autonomous college, which is at Trichy. And I always, recollect the things, the notifications available in our college. And I often willing to attend. And even in our busy schedule, I always would like to attend the events organized by the aeronautical department. And here our HOD sir is there. I am so blessed to see here in this event Arun Kumar Adik sir. A very good evening to all. Very good evening to you, sir.
Thank you. Thank you.
Fine, sir. I am so happy to see you. So in the alumni meet we have met, sir. And after that, here we have got a chance to meet you. And so with respect to the this 5 days FDP, it gone well. And I didn't skip any of the session. I have attended all the session. And the people you have chosen from various universities, various countries, and those people have been presented their content in a very well manner. And without doubt, they have been exposed their knowledges in the FDP topic you have been given. And it is very useful for me to do my coursework. And very thank you all for the people those who have been behind this FDP coordinator, HOD sir, and for your information, Dr. Gopinath sir is our aircraft structure sir. He has handled a subject for us. And Arun Kumar Adik sir is a HOD for me. And so during that time, we may get fear over him to talk, but here after completing that degree, he has helped us in a lot. So that's the thing. So I let other participants also give the feedback. Arun Kumar sir, Arun Adik sir, good evening to you. I would like to.
Yeah, thank you, Saravanan. Thank you for your wonderful and valuable feedback.
Thank you, sir. Thank you so much.
Yeah,
thank you, sir.
Thank you. So please, any other feedback from the participants? We have received a lot of questions from the participants during the sessions. Those people are here, so we love to hear feedback from them. Kindly, please. Yeah, we have some feedbacks in the chat box from Mr. Muralidharan on behalf of Department of Aeronautical Engineering from Surya Group of Institution. I thank the organizers and speaker for their valuable sessions. Thank you, Muralidharan sir. From Dr. C. Ramesh, Associate Professor, we thank you for your stimulating session. Thank you, sir. The Deepak Amarapalli, from Mr. Deepak Amarapalli, the sessions are more informative and enjoyable. Thank you for your feedback, sir. If anyone wish to share your feedback here in the open feedback session, kindly, the session is yours for another couple of minutes. Yeah, good evening, sir.
Good evening. I am Manivel Muralidharan from Kumaraguru College of Technology.
Yes, sir.
So the FDP was very useful to us in enlightening the various concepts associated with research, and right from the fabrication as well as testing and the various machine learning approaches. So everything neatly described and given in a lucid manner, which can easily take up for the research work. And I thank the Hindustan College of Engineering and Technology and the coordinators for conducting this well-organized workshop. So really it is an eye-opening for the researchers who are working in this area. So thank you, sir. Thank you for organizing such an informative workshop. Thank you, sir.
Thank you, sir. Thank you so much for your kind words and encouraging feedback. So anything else from the participants? Please, anyone else? From Mr. Layup Natarajan, really well session. Usually at starting, the FDP participants list will be high. After 1 or 2 days, participants count will be reduced. But for all the day, participants were very active because of the title. Thanks to the coordinator and supporting faculty. Thank you, sir. Thank you so much. We love to hear a few words from our former head of the department, Sir Arun Adak, sir, please.
Thank you so much for giving this opportunity to thank all the participants, that is one, and those speakers who have, the resource persons who have taken a lot of pains to educate the participants on the topics, on the various topics that has been put up. And I could not attend almost all the sessions, but from the feedback today that I got, it must be really good. Okay, and I'm extremely happy seeing this department growing with Dr. Gopinathan and the faculty members who have taken a lot of pains to ensure that this FDP program is a great success. Coming to all the topics that I just glanced through it, when I was given the invitation. Okay, right. The practical part of it, what I could, I being an old timer, we always talk of aircraft, I being from the aircraft stream, okay, and the fighter stream. I always talk about alcad materials and all that, but today, about 50 to 60% are composites, which I see in your FDP program, the topics that has been covered, advanced composite materials, and I'm sure that it has its own advantages. The advantages that the weight reduction of an aircraft, what we call it in a fighter stream, a clean aircraft, and with the composites, we can put a lot of loads, weaponry loads, okay, into it, so that the aircraft can go at a further distance and strike the enemy target. But there are a lot of limitations to composites materials. Maybe, I don't know, but the researchers here will take a lot of pains with that what one mechanical faculty member had said, that a lot of vibrations takes place, fatigue strength, fatigue loads of the aircraft. These are all practical situations that we faced in alclad stream, and I'm sure that we'll be facing now in the modern aircrafts too. But it is nice, and it is extremely informative, and I'm sure these research scientists, research papers that has been given now, okay, it will go a long way to improve the aircraft designs, aircraft materials, in improving the aircraft industry. Thank you so much. Thanks a lot for giving the opportunity. I must thank all the participants of this of FDP program, and I must thank all the faculty members, and including Dr. Gopinath, who has taken a lot of pains to ensure the FDP program is a success. I hope you all enjoyed it. Thank you so much. God bless.
Thank you, sir. Thank you for your kind and encouraging words. With continued support from you, we will definitely continue to work like this, and we will conduct such an events in futures too. So now I may request Professor Veera Manikandan to deliver the vote of thanks for this 5-day FDP program. Over to Veera.
Good morning. Good evening, everyone. Gopinathan sir is not feeling well. It is for information to Adak sir also and everyone. And for this reason, I'm delivering a vote of thanks as a moderator of this event and co-coordinator of the event. So here it's 5 days FDP has gone well, seriously, without any glitches of internet or anything. It's very proud of this one. And once again, I welcome and those who have been there, almost 130 plus participants as of now, and registered was nearly 380. And continuously we have been monitoring, and the floating population of this participant was around 280. So it was floating actually because of through online and those who are having online classes also. So irrespective of their online classes, we don't want to force them, and we have cancelled the tests also, and we have been forwarding the overall link of the participants' feedback after this session. On behalf of all the faculty members, HODs of Department of Aero, Hindustan College of Engineering and Technology, Dean, Principal, CEO, and Management, myself, Veera Manikandan, Assistant Professor, Aeronautical Engineering, as a moderator of this event, I am glad to express my vote of thanks here. First and foremost, I would like to thank all the participants. Because of them, it could happen huge success. And secondly, I would like to express my thanks to all the speakers, guest speakers. Overall, we have identified 10 speakers per day, 2 speakers. Most of them are from various backgrounds, like from North India, South India, abroad, like, and also the academicians, industries, and foreign researchers, IIT, Kharagpur, everyone we have accumulated over here, and we have gone to very much struggle in identifying also. And the second thank is that because not only for accepting our invitation for them, and they have given a lot of insights and knowledge sharing and skills they have shared very uniquely to all the participants. I hope every participant will agree also. And that was the extended thanks to all the 10 speakers of this FDP, 5 days FDP event. I'd like to mention each one of them here because I should not miss out anyone. So first day, first session, Devendran Trinavkarasu from ST Advanced Composites. He has given insights, very good insights about his composite and all. And then second day from IIT Kharagpur, Indrani Sen has given insights over her research. And third day from SRM Institute of Technology, Katanglotur, Dr. Gurdeshwar has given insights. Then second day afternoon, Dr. Dinesh Mohan from Nuclear Technologies. He has given. Then third day forenoon session by our alumni, Dr. Muthuram Prabhu Elanjayan has given very brief introductions about AI and this structural health monitoring and all from USA. And the afternoon session of the third day was given by Amasai Sengodan Ganapati from UK. And the fourth day from Tirunelveli Anna University, Dr. J. Bruce Alvin Rose. And the afternoon session of the fourth day was Satish Kumar Anushya Panusamy from UK. And the fifth day, today, morning session was given by again IIT Kharagpur, Dr. Chandrasekhar Tiwari, was given like biomimics of things of 3D printing and additive manufacturing. And now, not the least, Dr. N Venkateshwaran, professor in mechanical engineering, Rajalakshmi Engineering College, who is here now, has given many insights about his research work and all. So all those researchers who are all given many knowledge sharing things and shared various related to our FDP program on the topic advancements in aerospace material manufacturing, testing and characterization. And thirdly, I would like to thank the comparing committee, who involves many of faculties here, and collecting the profiles of all the speakers and all. And particularly, especially, I like to extend my thanks to Diksha Sambyal, who has delivered all his profile on the desk to all the participants. And lastly, I would like to thank the admin team of this providing net. Without any glitches, we have conducted this FDP because of them through online. So I extend all the thanks to them also for providing all the gadgets and everything to be here as a successful FDP over here. If in case I missed any of them personally or not mentioned here, it's a on and around thanks to all who are helped in in various teams. And this I end up with thanking everyone who are missed. Once again, I thank everyone. That's it today for today. And for this last announcement, I just want to give us all the sessions has been recorded and streamed in YouTube live. It is available in the channel, our channel, that is Agni Minds Aero ISET. It is mentioned as Agni Minds of Aero ISET. You can subscribe and you can have the insights of whatever you have missed due to this because of online or because of network issues. Once again, I inform the overall feedback will be shared after this session, and that will be collecting details for the certificate generation. Once if you fill the form, a certificate will be generated for us, and we'll be sharing based on the attendance. Last but not the least, I like to extend in sponsoring this event and giving a title on this event. Dr. E. Radhakrishnan, who was supposed to be given inaugural address, in his absentia, I thank him, and Dr. Tanige Arasu of HOD of Aeronautical Department, Aerospace Department, Madras Institute of Technology, is a society chairman. Okay, I thank him on this occasion, as well as treasurers. All everybody knows this Aeronautical Society of India is one of the leading society in India about aeronautical domain. So they have sponsored this event. In their logo, the certificate will be delivered to you on the complete submission of your report. So I thank Aeronautical Society of India, Chennai branch particularly for providing this sponsorship and all. Thank you once again to everyone who are missed, and thank you everyone. Thank you lots and lots to all the participants also. Thank you. This is the end of the session. Participants, you will be receiving a link of overall feedback in WhatsApp group. Session 10 will be shared in the Google chat itself, here itself. Both the links are available in the chat. Thank you, everyone. Thank you. This is the end of the session. Thank you. Thank you once again. Thank you lots.